Hope you guys are well today. If you are in the distance cohort today, you kind of drew the short end of the stick. You've got a hard day in front of you. These are not easy problems to solve. There's some of the tougher ones we've got to do all year. But if you mind your P's and Q's and dot your I's and cross your T's, you should be just fine. Those of you who are very methodical about setting up problems, you should do just fine with these. But they can be a little bit daunting the first time. So here you're seeing a physics teacher in his native habitat. I'm with some pulleys and whatnot. And let me just show you the setup I've got here. Okay. I have a setup. Let's move me up here. Let's move me over here. Okay. And I've got a setup here where I have 150 grams of mass down here. And I've got 200 grams of mass up here. And they're strung over a pulley right here. And what's going to happen is, I think you will figure this out, is that the 200 gram mass is going to drop and the 100 gram mass is going to raise. But I'm going to get a time here on this, and I want you to watch this, and then I'm going to walk you through what we know about this problem here. So let me get this set up, if you'll bear with me. And I'm going to stretch this over the pulley. I've got that skill set. And attach this down here. And this distance that this is going to fall is 1 meter. And this distance that this is going to come up will also be, surprisingly enough, 1 meter. So I'm going to start this and stop it once it gets to where it needs to go. Okay? And I got a time here of 1.25 seconds for that time. So keep that in mind as we go through this. I'm going to pause it here for a second and get a little bit more comfortable. So let's walk you how we're going to solve this problem. Okay? Since these two pulleys are attached to the same string, or the two weights are attached to the same string, they're going to accelerate at the same rate. The rate that this falls down will equal the rate at which this falls up. I know that seems kind of obvious in retrospect, but it might not be initially obvious when you first describe it. So here's the mass of the heavier object. It weighs 2 newtons. The mass of the lighter object weighs 1.5 newtons. So what we're going to do is we're going to draw a free body diagram of each situation here. Okay? But since they're both attached to the same string here, that means that the tension in this string is the same as the tension in this string. And we're going to represent that with a capital letter T. So if I were to draw free body diagrams of both, this is what we would see. Okay? The heavier object, we'll call that weight 1, is going to equal m1 times the acceleration due to gravity. And we're just going to represent the tension upward in the string. Otherwise, if it weren't attached to the string, it would just fall at the acceleration due to gravity. But it doesn't. There's a tension in the string. And the difference between this weight and this tension is going to be the net force. And the net force is what the mass is of that object, which is 200 grams or 0.2 kilograms, times its actual acceleration. So here I've got my first weight, I've got my mass, first mass times gravity, and that's going to be offset by the tension. On the right-hand side, now the tension is greater than the weight. Let's call this weight 2. I didn't quite write that there. That's why we can probably put that in there. We'll call that weight 2. And that weight 2 is going to equal this m2 times g. But this T and this T are exactly the same. They're the same string, so yeah, the tension in that string is going to be the same. But here the net force is acting upward. The tension actually exceeds this weight. And the difference between this tension and this second weight is also going to be the net force. But in this case, it's the net force of the second mass times acceleration. Don't be flamboozled here. This is just Newton's second law of motion. Okay? Again, if we cut this string, this weight would drop at this rate because there would be no force to offset it. But in this case, the tension is greater than this weight, so we have a net force operating this way. And I know that the net force always, by Newton's second law, equals mass times acceleration. Now what we're going to do is we're going to connect these two sides by this common currency of T. This tension is the same in the string. So we can make that a little bit interchangeable, as you're going to see here. So on my left hand side, my net force equals my weight minus my tension. My weight is greater than my tension, and I'm subtracting it. But in reality, guys, it really doesn't matter. If you select incorrectly which side drops, you're still going to be fine. It's all going to come out in the wash. So my net force here is the difference between those. So I'm going to rearrange this a little bit. Flop this tension over to this side, flop the net force over to this side. So my tension equals my first weight minus my net force. On this side, same thing, except now my net force equals my tension minus my weight. My tension is greater than my weight. So again, I flip-flop these around. Here my tension is the second weight plus the net force. Notice the subtle difference between this tension and this tension. Okay, so bear that in mind. So now I can set these two equal to each other. Since tension and tension is the same, I can set this first weight minus F net equals the second weight plus F net. But my F net in each case is going to be a little bit different because we've got different masses. So keep that in mind. So here's my weight. This first mass, which is 0.2 kilograms times gravity, minus 0.2 kilograms times whatever acceleration that is, equals this weight, which is m2g, plus m2a, the net force here. Again, this net force is not the same as this net force because they're different masses. Okay? So we're going to keep riding down this primrose path. I'm going to start getting like terms together. I'm going to toss this second mass over on this side, and I'm going to toss this net force over on this side. So all I've done is move this over here, move this over here, and now I'm grouping some like terms. I'm going to say that acceleration equals m2 plus m1, and that's going to equal this side. So what I'm going to do then is toss all this together. I'm going to divide this side by m2 plus m1 and set it equal to acceleration. So now you got to do some bean counting. 2 newtons minus 1.5 newtons, those are the weights of my two objects, weight 1, weight 2. Minus the mass of my two objects, I did 0.2 kilogram mass and a 0.15 kilogram mass divided by 0.35 kilograms. So if I end up with 0.5 in the numerator and 0.35 kilograms in the denominator, I'm going to find out that I would predict my acceleration to equal 1.4 meters per second squared. So how does that compare to our actual? Well, I know that delta y equals 1/2 at squared. I timed it as being 1.25 seconds, so I'm going to put that here. Let's put some parentheses around it, 1.25 seconds. Yikes. And you're going to find out that I end up with 2 divided by 1.56 seconds. So my actual acceleration here ended up being about 1.3 meters per second squared, which is a little bit less, but one thing we didn't account for was the fact that there is friction in the pulley and the fact that in spinning the pulley there's actually a different type of inertia that's involved with that, which we'll get to in the spring, called rotational inertia. So this data compares pretty favorably. We predicted 1.4 meters per second squared. We timed it to being 1.3 meters per second squared. So, again, not easy, guys. So this is problem 54 out of the book, and this is going to make the second one look like a rented mule. This is a little bit harder problem than the last one. I'm going to move this over to this side. So here's my setup. I have a 4 kilogram mass, and I have got a 9 kilogram mass that's resting on a slope that's at 40 degrees. And this mass slides down this slope a distance of 1 meter in 4.00 seconds. Okay, which means that this also must climb 1 meter in that 4.00 seconds. So, what do we do with this knowledge? First, let's find the acceleration. So, I know that one of my old toolbox equations is y equals 1/2 at squared. So I'm going to rearrange that. My acceleration equals, my acceleration is going to equal 2y over t squared. So in this case, acceleration is 2 meters divided by 16 seconds squared, because 4 meters squared is going to be 16.
So my acceleration here ends up being 0.125 meters per second squared. That's great, but that's not all that this problem wants. Just like a needy child, they want more and more and more. So now we're going to find the tension in the string. Okay, so if I want to find the tension in the string, and we're also, believe it or not, going to find our coefficient of kinetic friction, because there's kinetic friction operating on this slope that's preventing and impeding this progress. So what we're going to do here is going to be a little bit involved. We're first going to draw free body diagrams. This weight that's on the left-hand side, it's going to move up, so my tension is going to exceed this weight. There's going to be a net force operating in this direction. On the right-hand side, I've got a weight, I've got a normal force, I have a tension in the string that's going to be attached to that string, so this tension and this tension are going to be the same regardless of how I drew those arrows. Plus there's a force of kinetic friction acting up the slope. I wouldn't incorporate the net force in my free body diagrams, but I know that it's there because this slid down the slope, this had to rise on its string. So I know that my net force here equals tension minus weight. My net force here equals this component of gravity operating down the slope, which is m2 g sine theta, my mass times gravity times the sine of theta. It's a 40-degree slope, minus the tension in the string that's acting against me, minus the force of friction. Okay, you're not paranoid. Everybody is out to get you. Okay, these forces are acting against this going down the slope. My net force can be the difference between this component going down the slope, my tension, and my force of kinetic friction working up the slope. So I'm going to ignore this side for now. Just pretend that that doesn't exist while I walk you down this left-hand side. So here, my net force is this mass, my first mass, times acceleration. It's going to equal tension minus the mass times gravity. I'm going to rearrange this, put my tension by itself, and so tension equals M1. I'm going to use one of those math rules you learned about and clump together the A plus G. And so my tension here ends up being 4 kilograms. My acceleration, which we determined earlier, was 0.125 meters per second squared. I added that on top of G, so my acceleration plus gravity is 9.93. So my tension here ends up being 39.7 newtons. Guess what? My T equals 39.7 newtons. That's hunky-dory. But now we've got to use that to find mu k. So, on my right-hand side, I'm going to follow this out. I'm going to isolate this Fk because Fk is going to help me figure out what mu k is. So I'm going to isolate that. I'm going to toss it to the left-hand side, toss the net force over to the right-hand side. So now my Fk becomes a positive value rather than this negative over here. And this F net becomes a negative value. And now I can just do a little bit of bean counting. M2 g sine theta is 9 kilograms. It's a bigger mass over here. Here's g. Here's sine theta. I now know what tension is. That's 39.7 newtons. Minus my net force, which is 9 kilograms, times how much that box or that crate is accelerating down the slope. And I find that when it's all said and done, that means that my force of kinetic friction has to be 15.9 newtons. Mu k is Fk divided by Fn. Fn is mg cosine of theta. So I take 15 newtons divided by mg cosine 40. And so my mu k ends up being a very reasonable 0.23. Again, it's a dimensionless value. There are no units associated with it. So that's kind of a granddaddy of a problem. That's not an easy problem to solve. Your assignment for tomorrow based upon those two problems: 114, MC number 14, 117 number 28, and 118, 36, and 38. I am more than happy to answer questions that may arise. Good luck. You get to do labs on Thursday. On Wednesday, we've got to cover problems in elevators. That's going to be our last idea. We're going to get a test preview on Friday, and I think everyone's going to test together on Monday. We will see you later. I just beat the 15-minute timeline. Great.